In this video, we're going to take the given vector function, which currently is a function of t, and t as a parameter is often used to represent time, but it is possible to change the parameter, and what we're going to do here is to reparameterize this vector function and instead make the parameter arclength. And we'll use the variable s to represent arclength. Generally speaking, if we have some space curve traced out by a vector function r at t, we can calculate or say that the stretch of arc length that we're interested in is determined by how long we travel along the path. So let's say this was our initial position along the path, and then we had another position finishing the length of curve that we're interested in. And we would say here that the value of time goes from 0 to some value t. And as this value of t changes, that is going to have an effect on the length of the arc that is being measured. So we can say here that the arc length actually depends on how much time has passed. And the formula that we'll use is that starting at the value 0 of the parameter and measuring in the direction of increasing t, the arc length formula is r prime. Now, since we're using t as an upper limit, right, the output arc length depends on how much time has passed. And since we're using the parameter t as an upper limit, we can't use that in the integrand, so we'll just change to a different random variable, and u is what we're going to use here. So the length of arc that is traced out depends on how much time has passed, and then other than that, this is the same arc length formula that we've used before. So just for the sake of clarity, let's find r prime u, but before we do that, let's just change these variables to being u and change to being pointy bracket notation so that we can easily see r prime u is minus sine u, cos u, and then 1. And then the magnitude of r prime u is going to be negative sine u quantity squared is sine squared u plus cos u quantity squared is cos squared u plus 1. And again, we see that sine squared plus cos squared is 1, and 1 plus 1 is going to be 2 as the radicand. So our arc length that depends on how much time we let pass is going to be the integral measured from 0 to t. Rad 2 is the integrand, and then we're going to be integrating with respect to u. Now we have chosen an intentionally simple position vector function, one that when we take the derivative and the magnitude of the derivative function gives us a constant, so that we're integrating a constant value here. This has been intentionally chosen so that our calculations are not too complicated. The integral of this constant is just going to be the square root of 2 times u, and then we apply the limits of integration, which are from 0 to t. So the arc length that depends on t is rad 2 times t minus rad 2 times 0, which of course is just 0. So we end up with that arc length is equal to rad 2 times t. I'm dropping the functional notation on the arc length because the next thing that we want to do here is we want to solve for t in terms of s. So we'll divide both sides by rad 2 to get t is equal to s over rad 2. Now we have the parameter t in terms of s, and we can use this as a substitution in the original vector function. We're going to change all of these t's and substitute s over rad 2 in for each one of them. So as a reminder, our original vector function was cos t, sine t, and t. Now we'll just take s over rad 2 and we'll pop it in for each one of these t values here, so that when we do that, our vector function no longer depends on t time, but it now will depend on s arc length. So we'll end up with the cosine of t is the same thing as s over rad 2. Sine of t is the same thing as s over rad 2, we're subbing in here, and then s over rad 2 just gets subbed in for that final t, and here we have the vector function that has been reparameterized in terms of the arc length.